Hello everyone, in this video I'm going to derive some of the equations behind quantum tunneling. So tunneling is a situation where we have what we call a barrier like this, and we're imagining a wave coming in from the left with an energy less than the potential energy of the barrier, and we want to see what gets through. Because the wave coming in oscillates, but then in here the solution doesn't go immediately to zero, it exponentially decays. It actually can be a sum of a couple different exponentials, and we might have something coming out the other end. And so we want to investigate this and just see what kind of stuff happens. Let's add some more labels on here. This is our energy E. This is the potential, the barrier height, V naught. This will be zero energy. I'm gonna call this x equals 0, and I'll set this to be x equals, I'm gonna use capital L here. The book actually uses A, which I find a little confusing because they also use alpha. So I'm gonna call it L. But otherwise I have basically the same notation as in the book. And once again, as we have always done in the past, we are going to look at different regions and match up boundary conditions and basically figure out what happens from there. So we have region 1, region 2, and region 3. So here we have 3 areas. We want to write down the most general possible solution. In region 1, we are going to have our incoming wave and possibly a reflected wave. It can bounce back off this edge of the barrier and go to the left, so we have to include that. We have AE to the IKX plus BE to the minus IKX. What is K? Remember that K is square root 2ME over H bar in this case, because we just have zero potential there. In region 2, here we're going to have real exponentials, not complex exponentials. So here, I want to write the solution as CE to the, I'm going to call it alpha, as well as the book calls it alpha, plus DE to the minus alpha x. What is alpha? It's basically just the equivalent of K or K prime or whatever we want to call it, but I've just defined it here so that it's real. 2m v naught minus e, because that's a positive number that'll make this real, over h bar. And then finally, in region 3, the most general possible solution, I'm here back to zero energy, zero potential, so I can have capital E to the IKX plus F e to the minus IKX, where K is the same as in region 1. So once again, we match up boundary conditions, write down a bunch of equations, and try to solve it. So let's match up the boundary conditions. Actually, first, let's see if we can cross out any of these right away. We said this is the A, capital A is basically our incident intensity. We want to keep that, of course. Capital B is really a possibly a reflected wave, so we want to allow for that, so let's keep that. What about these exponentials in the middle? Normally, if these went off to infinity, we'd want to drop one of these to keep things from blowing up. But actually, neither of their boundaries are at infinity, so we actually have to keep both of these. We need both the capital C and the capital D terms, because both of these remain finite in that region. So the only one we can cross out here is that on the right side, again, we want to physically describe the situation where our particles are coming in from the left and moving to the right. And so we don't really want to describe particles coming from positive infinity and moving to the left. That means we don't want the left-going wave coming in from infinity, and so we're going to cross this term out. But now, basically, this is our transmitted wave, amplitude. And I think I've switched terminology a little bit from the book. They just swapped terms. They called this one F, then this one E, but it doesn't really matter. I want to write down all the boundary conditions. So actually, just because I like capital F better than E, why don't I just do that now? We're going to call this one F and this one capital E, but we're going to cross that one out. It'd be less confusing to have capital F than capital E. Anyway, but the point is we want to cross out the one that's going to the left. So let's write down our boundary conditions and put this together. Let me clear all this off. So we have two boundary conditions. We have our boundary for at x equals 0. That's a nice easy one to write down. There we had, so when we plug in x equals 0, that makes our exponentials just 1. So that makes things nice and easy. And so our boundary condition there is basically just that a plus b equals c plus d. That's what we get for plugging in x equals 0. That's continuity of the wave function. And then if we look at the first derivative of the wave function, we bring down a factor of what's in those exponentials. But there, that's going to give us an IKA minus IKB. That was the left-going wave, equals, and here we had real exponentials where we had alpha in the exponent. And so I don't remember how I even wrote it the first hand. Whether I wrote the minus alpha term first or the positive alpha, I erased it already. But I'm just going to match my notes here and say, write that. That's supposing that c was the coefficient of the minus alpha x. I don't remember if I wrote that on the previous slide, but we'll stick with that. That's matching up the boundary at x equals 0. Now we also want to match up the boundary at x equals L. This is just going to involve a bit more writing. Here we'll have c e to the minus alpha L plus d e to the alpha L equals f e to the I k L. And that's from matching the wave function, and matching the derivative gives us a minus alpha c to the minus alpha L plus alpha d e to the alpha L equals I k f e to the I k L. Okay. Now, as before, this looks like sort of a mess. It looks like we have 5 unknowns and 4 equations, but really we only care about things relative to the initial incoming intensity, which is A. So really there's only 4 unknowns that we want to find, B, C, D, and F. And actually, we don't really care. In this particular problem, we're not going to be very concerned with how much gets reflected or even what's happening in the middle of the barrier. So we don't really care about B too much. And if we need to find it, we can always look at the ratio of the transmitted. And we definitely don't really care about capital C or D. What we really want to find out is capital F and how it relates to A, because that's going to be the transmitted amplitude. And so if we want to figure out how much is actually getting through, that's what we need to find out. So next, what we need to do is basically look at all these equations and basically put them together until we can write F in terms of A. Now, I'm not going to write all this. It's basically a lot of algebra. There's nothing particularly deep or about the whole thing, but it's basically just piles, a page of algebra. You want to see it? There you go. Looks something like that. It's just a long derivation, but what you can do is you can kind of combine these 2 equations to get different expressions for C, plug them in, eliminate that, get 2 things involving A and B, get 2 equations involving F in terms of A and B, and then eliminate B, and so on. It's just a lot of steps. The final result is that you find, when you work all the way through, you find that when you look at the amplitude of f squared over the amplitude of a squared, which is really your transmission probability, then you get this expression. And here I want to emphasize there is a typo in the book here in equation 6-75. They left something out here, so you should know that when you look at this. You get this expression. Rather impressive looking expression. There's this hyperbolic sign thing. I'm using L here instead of A as the width of the barrier, just because I think it's easier to write and more clear. And you get some stuff that basically involving K and alpha, but you can combine that and rewrite them in terms of E and V naught in actually a bit of a simpler way. In the end, and that's all to the -1. So in the end, you get this as, and this is really your tunneling probability. Tunneling probability. So if you remember hyperbolic sine, I mean, that's something you have in your calculators anyway, but it's basically related to real exponentials. Hyperbolic sine is e to the x minus e to the minus x divided by 2. So if you plug that in, but this is a nice compact way of writing that. So you see, you get this tunneling probability. The important parts of this are that the width of the barrier, which I called L here, that's the physical length, it's in distance units, only comes in here in this sinh squared, but this thing has exponentials in it. So really this is hiding the exponential. So there's this kind of exponential behavior of the tunneling probability with respect to the width of the barrier. The thicker your barrier is, the tunneling probability just goes down exponentially. So that's very fast. You can see a lot of tunneling through narrow barriers, and then you make it even twice as thick, and it just goes down exponentially. The tunneling probability goes to nothing. There's also some dependence on the relative energies of the things involved. There's these E's over V naughts that show up. And that's actually, there's also some E and V naught hidden in alpha. But it's less sensitive to that. What it's really sensitive to is this capital L. There is, nicely, and here, a nice approximation because this thing has exponentials in it. When alpha L is reasonably large, you can make some approximations. And what does reasonably large mean? It means alpha L just sort of larger than 1. So 3 is actually probably reasonably large for those purposes, more than 3 or 4, because again, this thing involves exponentials, and by the time you get to e to the 4th power, that's already a fairly large number. And so if you have this, then you can make an approximation. What is the approximation? Let me clear off some top here. It's a little less cumbersome to calculate. And the approximation, let me just emphasize here, that this is approximation when alpha times L is greater than 1. That's what I mean by that up there, is that this is about 16 E over V naught, 1 minus E over V naught, E to the minus 2 alpha L. And there it's really clear. This exponential is really just coming from this sinh squared, but the idea is in this limit it simplifies a bit, and you get this expression. So this is actually, in practice, more often used because often you are in that approximation, but you'll note that it is something that you should check. Tunneling is a real thing that's observed in nature. Not only is it observed in nature, it's actually used a lot. If you've heard of a electron microscope, scanning tunneling electron microscope. Sorry, I'm tripping over that. STEM. Um, they actually let me. They measure the surface of materials, and how does that work? Is you break a piece of metal into, you kind of snap it, and when you snap a piece of metal, you tend to get a sharp tip. So you get piece of metal, a conductor. It has a sharp tip. Electrons can flow here, but the rest is an insulator. And then you have a surface that you're trying to measure. And the surface in this case, for this particular technology, the way you have to do the surface also has to be a conductor. But there's ways around that. You put a voltage, you hook a battery up to make a voltage between these two conductors, and you actually tunnel electrons through this barrier. This acts as a barrier here because air or vacuum or whatever is an insulator. There's effectively a potential barrier there. But if it's really narrow, you get a current. The electrons can tunnel, and you get an electrical current. And actually, the way the instrument works is it sets up a feedback loop such that if there's no current flowing, it moves. There's a little motor up here that moves this down until the current starts flowing. And then once the current starts flowing, if it flows too much, it moves it back up. And so then by basically measuring how much that tip has moved up or down as you scan back and forth, you get a very accurate, precise measurement of the surface of this material on the atomic scale. And so that's a really neat technology. It's been used for decades, refined in a number of ways to make even more interesting measurements. But the fundamental physics behind it is tunneling of electrons. These electrons are in a conductor, and they're just basically tunneling through to another conductor down here, right through a barrier that has a potential energy much greater than their energy. So that's pretty interesting. One of the other areas where tunneling was used to explain things is in some situations of radioactive decay within the nucleus. People were like trying to understand why occasionally a nucleus would break apart and send out an alpha particle. And one way of imagining how that happens is you actually look at it as a process. But that we'll talk about more, maybe live in lecture. So thanks for watching.